Okay, let us continue with the carbonyls. In the last class, we had a very general look at the carbonyls, and we discussed the possible binding modes of carbon dioxide to a transition metal. Now let us more closely look which carbonyls are being realized in nature and why. So to start with, let's first look at the most simple carbonyls, and let's understand how their structures are being guided. All right. So generally, for carbonyls, the 18 electron rules with a few exceptions. So we need to think about, well, how many ligands, carbonyl ligands, do we need to place around transition metal so that the 18 electron rule is fulfilled, and which structures will result. So generally, we need to distinguish between carbonyls with elements that have an even electron number and carbonyls with elements, meaning metals, having an odd electron number. So why is that? Because in the most simple carbonyls, we consider the carbonyl as a 2-electron donor. So the carbonyl will make a simple metal carbon bond between the carbon atom and the metal, whereby the carbonyl binds end on to the metal. So now when the carbonyl is a 2-electron donor, and we need to fulfill the 18-electron rule, then it becomes immediately clear that we can fulfill the 18-electron rule only when the element has an even electron number. Because an even electron number plus 2 times an integer number, whereby the integer number represents the number of carbonyls, can give 18. When we start out with an element that has an odd number of electrons, then no matter how many 2-electron donor carbonyl ligands we add, we can never arrive at 18. We can either arrive at 17 or we can arrive at 19. So in this case, the carbonyl, or the most simple carbonyl, is not a monomeric carbonyl, but a dimeric carbonyl, because 17 valence electrons dimerize to make a dimeric carbonyl with a metal-metal bond. Okay, so let's summarize this up. When we have elements with an even electron number, then we can make a simple mononuclear carbonyl of the formula MCOX. However, when we have metals with an odd number of electrons, then 2 17-valence electron fragments dimerize to form a carbonyl with the formula M2COX. There's one exception, which is the vanadium hexacarbonyl, which does not dimerize, and we will understand shortly why this is. All right, so let's start with the first group, the carbonyls of elements that have an even number of valence electrons. And let us start out with the 6th group elements, which are the chromium, molybdenum, tungsten. So which formulas and structures would we expect for carbonyls of chromium, molybdenum, and tungsten, assuming that the 18-electron rule holds? Okay, so we know that we need 18 electrons. So we further know the number of metal electrons. So we are in the 6th group. So that means that we have 6 valence electrons. So now how many electrons do we need in order to get to 18 electrons? Well, we need 12. So we also need to consider the charge, but the charge will be 0 because we will look at neutral carbonyls here. But now let's count the number of ligand electrons. So we have 6 here, so we need, well, 12 in order to get to 18, because 18 minus 6 is 12. So now how many carbonyl ligands do we need? So we consider here the carbonyl as a 2-electron donor, and therefore the number of ligands needed is just, well, the 12 electrons divided by 2, this is 6. So this is why we would expect a hexacarbonyl of the composition MCO6. Such a carbonyl should be an 18-electron complex and thus be stable. Which structure would we expect? Well, for the coordination number 6, you know that the octahedral structure is the by far most preferred structure. We have no reason to assume why another structure would form. And indeed, these compounds make octahedral structures. So all these 3 carbonyls, the chromium, the molybdenum, the tungsten hexacarbonyl, are stable, crystalline, sublimable solids made of MCO6 octahedra. So now let us ask, how could we realize other octahedral carbonyls with CO6 ligands with elements other than chromium, molybdenum, and tungsten? So now we could, for instance, go to the left in the periodic table and go from the chromium to the vanadium. So the vanadium has 1 electron less than the chromium. Therefore, if you want to realize an octahedral hexacarbonyl compound, then we would need to give this carbonyl a 1 negative charge. Does this carbonyl exist? Yes, this carbonyl exists in nature. So what about the higher homologues? Also the higher homologues, the niobium hexacarbonyl minus and the tantalum hexacarbonyl minus exist as well. So now we can go systematically through the periodic table using the same principle. So we can go further to the left in the periodic table. And the element to the left of the vanadium is the titanium. The titanium has 1 electron less than vanadium. So in order to realize an 18-electron hexacarbonyl, our carbonyl would need to carry a 2- charge, and indeed such a carbonylate anion is realized in nature. So are the higher homologues, the zirconium hexacarbonyl 2- and the hafnium hexacarbonyl 2-. Now, can we also go into the other direction of the periodic table? So the element right to the chromium is the manganese. So the manganese is 1 electron more than the chromium. Therefore, in order to make an 18-electron hexacarbonyl, our hexacarbonyl would need to carry a +1 charge. Indeed, such a carbonyl is known to be stable. So what about the higher homologues? Also the technetium hexacarbonyl plus and the rhenium hexacarbonyl plus are stable. So if we further go to the right in the periodic table, we go from the manganese to the iron. But the iron has 1 electron more than the manganese. Therefore, our carbonyl must have a 2+ charge instead of a 1+ charge. So this carbonyl cation is also stable. And well, the higher homologues, the psenium and the osmium, are stable as well. So can we go further to the right? Let's go from the iron to the cobalt. The cobalt has 1 electron less than the iron. For that reason, we need a 3+ charge at the octacarbonyl cation here. However, when we look if nature does make this compound, we realize nature actually doesn't make this compound according to the 18, despite it fulfills the 18-electron rule. It also doesn't make the rhodium compound. However, the iridium compound is known. So this behavior reflects a general trend. So we can make relatively easily carbonylate anions, even of high negative charge, but we cannot easily make carbonyl cations, especially not when they have a high positive charge. So high positive charge tends to destabilize a carbonyl. So now why is that? We have given the answer actually on in the previous lecture. We have seen that when the carbonyls have a high negative charge, then they can be stabilized by pi acceptor interactions, which is also called pi back bonding. And that pi back bonding increases the bond order between the metal and the carbon. And that overall stabilizes the molecule. The more we go toward a positive charge, the lower the bond order between the metal and the carbon. And for highly positively charged carbonyls, such as the hexacarbonyl cobalt 3+, we have destabilized the cobalt carbon bond so much so that the entire molecule is not stable anymore. So is there actually also experimental evidence for the weakening of the metal carbon bond in these compounds? And there is, we can see this by IR spectroscopy. And I'll show you here the wave numbers for the CO stretch vibration. So you've learned in the last class that as we strengthen the metal carbon bond, increase the bond order between the metal and the carbon, we decrease the bond order between the carbon and the oxygen. And as we decrease the bond order between the carbon and the oxygen, we also decrease the wave number of the associated CO stretch vibration. And so you see, therefore, that the wave numbers of CO stretch vibrations, as you go, for instance, from the iron hexacarbonyl to the titanium hexacarbonyl, continuously decreases. So here from 2204 to 2100 to 1986 to 1847 to 750. So this is experimental evidence that the CO bond order really increases and the metal carbon bond order really increases as we go here from the cobalt to the titanium, and this explains the increased stability of the carbonyls as we go to the left of the periodic table. You see, the same is actually also true for the higher homologs. Also here, the CO stretch vibration decreases from about 2200 to about 1750. The same is also true for the third series, where the bond order, these stretch vibration decreases from 2205 numbers to approximately 1750 wave numbers. Okay, so now we have understood hexacarbonyls and their relative stability also. Now let us go from the 6th group to the 8th group, and let's see what neutral carbonyls we would expect for the 8th group. So which elements do belong to the 8th group? So this is the iron, the ruthenium, and the osmium. So how many carbonyl ligands would we expect for these elements? Well, we can again apply the 18 electron rule in order to determine this. So we need, again, 18 electrons. So the metals, in this case, contribute 8 electrons, okay, because they are group 8 metals. They have 8 valence electrons. So again, the charge of the carbonyl shall be 0. And then the number of ligand electrons that we need to go from 8 to 18 is, well, 18 minus 8, that is equal to 10. So assuming that our carbon ligand is again a 2-electron donor, the number of carbonyl ligands is just 10 over 2, which is equal to 5. So therefore, we would expect pentacarbonyls for these metals. And indeed, iron, ruthenium, and osmium form neutral pentacarbonyls. So which structures could they have? So we have seen that there are two structures for the coordination number 5, which are approximately equally stable, the trigonal bipyramidal structure, as well as the square pyramidal structure. In this case, the trigonal bipyramidal structure is favored, and these molecules accordingly exist in this structure. So all these compounds are liquids. So the iron pentacarbonyl is a light orange liquid. The ruthenium and the osmium pentacarbonyl are both colorless liquids. So now we can ask again, can we also make pentacarbonyls with other elements? The answer is yes. We only need to adjust the charge at the carbonyls so that an 18 electron complex results. So again, we can first go to the left in the periodic table, starting from the iron. So to the left, we have the manganese. Because the manganese is 1 electron less than the iron, the respective pentacarbonyl must have a 1- charge in order to fulfill the 18 electron rule. So as we go further to the left in the periodic table, well, first of all, also the higher homologs exist, the technetium and the rhenium pentacarbonylates. As we go further left to the periodic table, we have the chromium. The chromium has 1 electron less than the manganese, and therefore the respective pentacarbonylate must have a 2- charge. Or the higher homologs, the molybdenum pentacarbonylate and the tungsten pentacarbonylate 2- exist. So further, when we go from the chromium to the vanadium, then because the vanadium has 1 electron less than the chromium, the respective carbonate has a 3- charge instead of a 2- charge. Also, again, the higher homolog, the niobium, and the tantalum compounds exist and are pretty stable anions. Okay, now what about the other direction? As we go to the right in the periodic table, and as we go from the iron to the cobalt, because the cobalt has now 1 electron more than the iron, the respective carbonyl ion must have a 1+ charge. So this weakly positively charged carbonyl cation is known to be stable. Also, the higher homolog, the rhodium and the iridium compounds are known to be stable. Okay, so now as we go from the cobalt to the nickel, we would require a 2+ charge, but in this case, the 2+ charge is already too high in order to make the respective carbonyls stable. The nickel carbon bonds are already too weak in order to provide a stable compound. Also, the higher homologs, the palladium as well as the platinum compounds are not stable. So again, we see here the effect of the weakening of the metal carbon bond due to the weaker pi acceptor interactions possible. Okay, now let's go to group 10. So in group 10, we have the nickel, the palladium, and the platinum. So again, we will need 18 electrons. We have, in this case, 10 metal electrons because we are in group 10. So we again have no charge. We assume these carbonyls to be neutral. Now, the ligand electrons that we need is, well, 18 minus 10, and that's 8. So how many ligands will we need? That's just 8 electrons divided by 2, that's 4. So in this case, we would expect tetracarbonyls to be stable. So these carbonyls are tetrahedral, have a tetrahedral structure. It's the most common structure. I would understand that here the tetrahedral structure is favored over the square planar structure, because we know that square planar structure requires 16 electrons, but here we have 18, therefore the tetrahedral structure is being favored. So now in this case, the nickel carbonyl does exist as a colorless liquid. It has actually a very low boiling point of 43 degrees Celsius, so it's actually quite volatile, whereas the respective palladium and the platinum compounds are already unstable. So this reflects another trend, which is that generally, as we go to higher periods, the respective carbonyls tend to get more unstable because of the less effective orbital overlap between the large metal orbitals and the relatively small highest occupied molecular orbitals at the carbonyl ligands. Okay, so now what about charge structures of the composition metal CO4? So again, we just need to adjust the charge in order to fulfill the 18 electron node. So let's just do this again. First, let's go to the left in the periodic table. We go from nickel to the cobalt. The cobalt has 1 electron less than the nickel. Therefore, the tetracarbonyl needs a 1- charge. Are the higher carbonylates stable? The answer is yes, but in this case, for some reason, my animation follows a different order. So we first go here from the cobalt to the iron. So the iron has 1 electron less than the cobalt, so we need a 2- charge. So we can further go from the iron to the manganese. Then because the manganese is 1 electron less than the iron, the respective tetracarbonyl needs a 3- charge. Finally, we can even go to the from the manganese to the chromium, and then our respective anion has a 4- charge. So you see that high negative charges are no problem, just because the higher the negative charge, the stronger the pi accepting interactions between the carbonyl ligand and the metal, and the higher the bond order and the higher the stability. Okay, so now here you see that all the higher homologues are also stable, and you see again the stabilizing effect of the negative charge. So while for the neutral compounds, the metal carbon bond is already too much weakened. Remember here also that for the tetrahedral structure, we cannot make real pi interactions because the orbital orientation is just not appropriate. Remember, we discussed pi interactions of tetrahedral complexes when we talked about ligand field theory. So that here already the pi acceptor interactions are too weak in these neutral compounds in order to make these complexes stable. So when we go in the other direction and go to the copper, then the copper tetracarbonyl plus is still stable. However, again, the higher homologues are not stable. All right, so now let's summarize this. So as we go from group 6 through group 8 to group 10, we go from hexacarbonyls to pentacarbonyls to tetracarbonyls. The stability tends to decrease. That is because the pi orbital overlap decreases from group 6 to group 8 to group 10, just because the pi orbital overlap is best for the octahedral structure. It's less effective for the trigonal bipyramidal structure, and it's least effective for the tetrahedral structure. So this explains this trend. And the other trend is that the stability tends to decrease with a period. And that explains the instability of the palladium tetracarbonyl and the platinum tetracarbonyl. In this case, the mismatch of the orbital sizes together with the inefficient pi orbital overlap due to the tetrahedral structure destabilizes these compounds so much so that they become overall unstable. Okay, so finally we can ask, well, what about group 4 and group 12 carbonyls? So all of these are non-existing, and we can think about why. And that's a question to you. Can you imagine why group 4 and group 12 carbonyls are non-existing? You may unmute yourself. Nobody has an idea? So how many carbonyl ligands would we need for the group 4? If we again apply the 18 electron rule.
7.
7, correct.
Is it because the coordination number becomes too large and the structure will become unstable? Yes,
this is exactly the reason. Very good. So a coordination number of 7 is too large for carbonyl. And therefore, the group 4 carbonyls just don't exist for that reason. Now, what about the group 12 carbonyls? How many carbonyl ligands would they need?
3.
3, correct. And that's a low coordination number, which is also not very favorable. Okay. So for group 4, 7 ligands are needed to achieve 18 electrons, and so the coordination number is too high. And for group 12, 3 ligands are needed to achieve 18 electrons, and the coordination number is too low. Okay, so now let's move over from the carbonyls that have an even number of valence electrons to those that have an odd number of valence electrons. So now, for some reason, my Zoom meeting has again disappeared here. So I just solved the problem the way I solved it last time. It's really very annoying. So yeah, here I am back. So now I want to screen share. You can all still hear me?
Yes, we can hear you.
Very good. Then we are still in the same meeting. Excellent. And now go to the homoleptic carbonyls of the 7th group. Okay, the 7th group is a group in which there's an odd number of valence electrons, and the elements manganese, technetium, and rhenium belong to them. So now, in this case, as I said before, we need to create 17 valence electron fragments and then dimerize these 17 valence electron fragments. And then we need to look, well, what structure would we expect? Okay, let's do our electron counting. So in this case, we need 17 valence electrons. So our metal our metal provide how many electrons? Well, in the 7th group, our metal would provide 7 of them. And now we have, again, no charge. We assume that these are neutral carbonyls. So the number of ligand electrons needed is then just the difference between 17 and 7, and that's 10. And then the number of ligands needed is just 10 over 2, which is 5. We would have to dimerize 2 pentacarbonyl fragments to form a dimer. Okay, so now you can see this here. So we have here 2 pentacarbonyl dimers that are being combined via a metal-metal bond, and then that gives then a carbonyl of the composition M2CO10. So now, which structure does such a carbonyl have? So this structure is derived from an octahedral structure. So you see that each manganese is surrounded in an octahedral way. You see here 1, 2, 3, 4, 5 ligands are carbonyl ligands, and the 6th ligand is then the second carbonyl fragment, and you see that because of that, the manganese is surrounded in an octahedral way. So the other manganese is also coordinated in an octahedral way. Again, we have 5 CO ligands, and then the other carbonyl fragment is our 6th ligand. So that means that overall we have to distinguish between axial and equatorial ligands. So we have here these 2 carbonyls as the axial ligands, and we have here these 4 as equatorial ligands, and these 4 as equatorial ligands as well. So now, when we look at the relative orientation of the equatorial ligands, then we see that they are in staggered orientation relative to each other. So this square here is rotated by 45 degrees relative to this square over there, and we can understand this very easily. There's steric repulsion between the carbon ligands, and they try to minimize the steric repulsion by going into the staggered orientation. All right. So now, can we also form charged carbonyls of the composition metal 2CO10? So let us do the same exercise as previously. Let's go from the starting from the manganese to the left in the periodic table. And we see that as we do this, my animation works a little differently again. So I can summarize first the result and then illustrate the result by the example. So generally, there are no highly charged binuclear carbonyl anions in this case. So we can make weakly charged ones, but not highly charged ones. And the reason is that the negative charge stabilizes the metal-carbon bond, but too much of a negative charge starts to destabilize the metal-metal bond, because formally we accumulate negative charges on the metal. Therefore, we can only have weakly charged carbonylates, but not strongly charged carbonylates. So we cannot have any carbonyl cations in this case, because even weakly positively charged carbonyl cations have too little of a bond order between the metal and the carbon. In addition, also the 2 positive charges on the metals, they repel each other, and therefore counteract the stability. All right, so now to the examples. So if we go from the manganese to the chromium, we have each chromium having 1 electron less than the manganese. So when we have 2 metals, we have 2 charges to consider. And therefore, the respective anion has a 2 negative charge. So the higher homologs also exist, the molybdenum and the tungsten, but we cannot make any more highly negatively charged carbonylates for the reason that I discussed. A 4- charge would already destabilize the metal-metal bond too much. So now let us go from the 7th group to the 9th group. In the 9th group, we find the elements cobalt, rhodium, and iridium. So let us count again the electrons. We need 17 in this case. So how many do the metals contribute? Well, they are in the 9th group, so they contribute 9 electrons. So now how many electrons do the ligands need to contribute? Well, the charge again is 0. So the number of ligand electrons needed is therefore, well, 17 minus 9, and that's 8. And then the number of carbonyl ligands needed is, well, 8 over 2, which is equal to 4. So for that reason, we would expect M's metals tetracarbonyl fragments dimerize to form a dimer with a metal-metal bond. And that's exactly what we get. We get dimers of the composition, well, M2CO8. And the structure of these dimers is derived from a trigonal bipyramidal structure, because each metal is surrounded by 5 substituents. Okay, so these are 1, 2, 3, 4 carbonyl ligands, and then the 5th substituent would be the other carbonyl fragment here. Okay, so for the other cobalt, the same. We have 1, 2, 3, 4 carbonyl ligands, and the cobalt carbonyl here would be the 5th ligand. So now you see again we have to distinguish between equatorial and actual ligands. You see again we have here these 2 actual ligands. In this case, we have 3 equatorial ligands here and 3 more equatorial ligands over there. That gives overall 6. So again, these equatorial ligands, they stand in a staggered orientation to each other in order to minimize the steric repulsion. Overall, the point group of such a molecule is D, 3D. I would like to point out that an effect that we have previously observed already for compounds in which we have the coordination number 5 is here seen again. So these structures are fluxional. So they constantly exchange their ligands. In addition to this structure here, there's another structure here which exists in addition. And these 2 structures here are in equilibrium. And because the coexistence of these structures, we have the constant ligand exchange. Okay, so now what is different in this structure in comparison to that structure? So in this structure here, we have only 3 terminal ligands surrounding the cobalt, but there are 2 bridging ligands surrounding the cobalt as well. So that actually increases the coordination number around the cobalt from 5 to 6, and this is the driving force for the stability of this structure here. So in solution, there's a dynamic equilibrium between these two, but in solid state, you even find this structure with the bridging carbonyl ligands exclusively. So because of the dynamic equilibrium solution, we have a constant scrambling of carbonyl ligands, because a carbonyl ligand can, well, change from, well, terminal to bridging, and then just the other carbon cobalt bond cleaves, and then this carbonyl ligand becomes a terminal ligand at the other cobalt. Of course, that process is reversible, so that all the carbonyl ligands can actually scramble back and forth. All right. So this structure here, which belongs to C2V, as I said, is present in the solid state exclusively. That indicates that this structure here is actually even a little bit more stable than this structure. And we can explain this because here we have a coordination number 6, while here we have only a coordination number of 4. So let us ask the question, well, can we also make charged carbonyls of that type? Again, the same rule as previously holds. There are no highly charged binuclear carbonyl anions, and there are no binuclear carbonyl cations at all. And the same reasons as discussed previously holds. Too high of a negative charge stabilizes the metal carbon bond, but destabilizes the metal-metal bond. For cations, the positive charge both destabilizes the metal carbon bond as well as the metal-metal bond. Therefore, no carbonyl cations exist. So therefore, we only know these 3 species: the iron, ruthenium, and osmium carbonyls. These have all a 2 negative charge, because as we go from the cobalt to the iron, we add 1 electron per metal, but we have 2 metals, so we have to add 2 electrons. All right, so let us go to the 11th group also. In the 11th group, we have the copper, the silver, and the gold. So what structures would we expect? Well, we will again need 17 electrons. The metal electrons, we have in this case 11. So how many do we need, given that the charge is 0? How many electrons? Well, that's 70 minus 11. Well, that is 6. So how many carbonyls do we need per 17 valence electron fragment? Well, that is 6 over 2, which is equal to 3. So we would expect tricarbonyl fragments dimerized. And you see this here for the nickel. We have here this nickel tricarbonyl fragment and this nickel tricarbonyl fragment, which is dimerized. You see that, well, in this case, we need a 2 negative charge. That is because the nickel has 1 more electron, the copper, the silver, and the gold. In this case, neutral carbonyls are actually not stable. So the copper, silver, and gold compounds of the composition M2CO6 are not stable, because even in the neutral state, the metal carbon bond is already much too weakened. But a slightly negative charge is actually ideal. For that reason, the respective nickel compound with a 2 minus charge is actually existing. Okay, so we can also determine a stability trend for the dimer carbonyls, and the stability trend is similar to those for the mononuclear ones. So again, as we go from the left to the right in the periodic table, the stability decreases. So the manganese and the cobalt are known, but the copper is not known, again, because we go from the coordination number 6 to 5 to 4, and as we lower the coordination number, the pi orbital overlap decreases, so the pi accepting interactions become weaker, which destabilizes the carbonyl. So again, we see stability decrease also for the higher homologs of the orbitals. So as the period increases, the stability also tends to decline because the large metal orbitals don't overlap so effectively anymore with the relatively small homos of the carbonyl ligand. So this explains the instability of the rhodium, iridium, copper, silver, and gold carbonyls. Okay, finally, let us have a look at the group 5. So in the group 5, we have the vanadium, the niobium, and the tantalum. So in this case, we would require a hexacarbonyl fragment because, well, how many electrons do we have to add to 5 in order to get 17? Well, that's 12. And well, when you need 12 electrons and each carbonyl is a 2-electron donor, then we need 6 carbonyl ligands. So now, in principle, we should also need to dimerize this compound. But in this case, no dimerization takes place because the coordination number would become too high. The coordination number would become 7, and the carbonyl is so much like the coordination number 6 in the octahedral shape. Therefore, the vanadium hexacarbonyl stays alone as a radical compound, which is violet, whereby the radical electron remains sterically inactive, and that explains the octahedral shape. So this carbonyl can, of course, be easily reduced because then we go from 17 electrons to 18 electrons. So the vanadium hexacarbonyl is therefore known to be an oxidant. It likes to accept electrons from other chemicals it reacts with, and it can also be used as an oxidant in synthetic chemistry. So the higher homologs, the niobium, the tantalum, are not known. We can explain this by the fact that orbital overlap between the heavier elements and the carbon decreases. So the vanadium hexacarbonyl is already not so stable because it's a 17 valence electron compound, and it's further destabilized when we replace the vanadium by niobium and tantalum, respectively. Okay, then let us stop at this point. So I just